Okay, welcome everyone to this fourth and final oral presentation session, this time on the theme of reinforcement learning for control and game theory. I know it's a final session and we're already behind. I don't want to eat into the coffee break, so let's just crack on. It's my pleasure to introduce the first presenter, Professor Tamer Başar from UIUC. We'll be speaking on the theme of convergence in full information general sum Markov games.
Thank you. Thank you. And good afternoon. I know it's late in the conference, and this piece of work actually is the brainchild of the first author, Weichao, who was a PhD student of mine. I say was because he graduated in May and joined a company. In the initial startup phases, it was difficult for him to travel and also some visa issues. Otherwise, he would have presented it. The second author was also a PhD student at Illinois, and he also graduated in June, 1 month after Weichao, joined industry again, software. So they're applying all this reinforcement learning in a game theoretic context at their current jobs. And the next two co-authors are from IBM. Actually, we have a major project with IBM on serverless computing, and this is on the theory side of that work. And then Zbigniew is a colleague of mine at Illinois. So as far as I can tell, this is actually the first paper in the presentations here at this conference that deals with games, and particularly with Markov games I'll be talking about. And when you go from, in the context of reinforcement learning, from control or single agent optimization to games, there are new, of course, equilibrium solution concepts that emerge. So multi-agent reinforcement learning is definitely something that's around us, and you have heard a lot about it. And agents are strategic when many of them are interacting within a shared environment. And there have been successful applications of this in the Go, poker, and real-time strategy games. And one of the sort of metrics that one uses in the learning aspect of such games is the no-regret learning. A learner, in this case, aims to maximize the cumulative utility with respect to possibly adversarial outcome sequence of the environment. And this is connected to game theory for finding solutions under various equilibrium concepts. As I said, if you have a single agent problem, then you're essentially optimizing a single objective function, whereas when you move to games, there are multiple solution concepts. So I won't be able, because of the time restrictions, go into the details of the proofs and so on. So I'll give you some punchlines here and some of the highlights of this work and where its contribution lies in this broad landscape. Now, when you talk about games, you can talk about normal form games as well as Markov games. So these are the two sort of main classes of games. There are, of course, others. Some of the folklore results in the context of normal form games is that if all players run no-regret algorithm with a square root of t adversarial regret, then there is an 1 over square root of t in that order approximate Nash equilibrium in two-player zero-sum games, or 1 over square root of t approximate Coarse correlated equilibrium in general sum games. Now, I should mention that when we talk about Nash equilibrium, that's a mixed strategy Nash equilibrium. and that's due to Nash in the 1950s, which is an extension of what von Neumann did in 1928, the minimax theorem from zero-sum to non-zero-sum games. But the players there are, their strategies are not correlated. And then Ullmann introduced the notion of correlated strategies or policies, and which led to correlated equilibrium. And then there was a further sort of extension of this, which is a sort of a looser solution concept, which is called coarse correlated equilibrium. So I'll be referring to these three sort of types of equilibria: the Nash equilibria, mixed strategy Nash equilibria, correlated equilibria, which I'll use the acronym CE, which comes next, and then the coarse correlated equilibria. And so in obtaining these results for normal form games, there was a broad family of algorithms have been used: the multiplicative weight updates, and follow the regularized perturb leader, and FTRL, and there is an optimistic version of this which we are using, which is OFTRL, and then the mirror descent. And we have actually, in a recent paper at NeurIPS in last year, we have used it for meta-learning in games. Under full information self-play, we have square root of t order regret, which is really unimprovable against an adversarial environment. And for learning in games, each player actually does not face adversarial payoffs, but rather interacts with other players. So different sort of formulations have been introduced in this context, one of which is self-play, and which assumes that all players are using the same algorithm. And most of the order sort of convergence results are based on self-play, as well as full information, which means that the players have access to the full state information, as well as they can interact with a coordinator or an oracle that provides the rewards that would be attained under different choices of the actions. And then there is the EGT, excessive gap technique of Nesterov, which have been used in convergence to two-player zero-sum Nash equilibria, and which is in the order of, again, 1/t. I have the tilde here means that the log factor has been suppressed in all these. And then there is the optimistic FTRL. Now, when we move on to Markov games, from normal form games to Markov games, there are results and banded feedback, where in two-player zero-sum games, it's again in the order of 1/square root of t and some log factors. And in general sum games, it's again, for both CC and CE, it's in the order of 1/square root of t. Now, with full information feedback and self-play, it has been shown in fairly recently, in 2022, actually, the first keynote speaker, Lena, was one of the authors in that paper, which appeared in the NeurIPS in 22. In two-player zero-sum games, you have 1/t convergence, whereas when you go to, this is for zero-sum games, when you go to general sum games, of course, there is the CCE and CE, and the order relationships there is 1/t to the 3/4 and 1/t to the 1/4. So this table actually summarizes the one in black font, the state of the literature as of last year. And then we looked at this table and we said, well, can we complete this and fill up the gaps? Everything is in the order of 1 over t for normal form games, as well as Markov games, but with zero-sum. Well, is it possible to obtain, again, a 1 over t, 1 over t? And that's the main contribution of this paper. So in a sense, you may, when you look at this picture, you may say, well, there isn't much else to be done because everything is in the order of 1 over t. Still, I'm going to share with you, I have very limited time, the actual bounds, and there may be some log terms there that could be shaved off, and that would be the additional contribution of future research. So, no regret learning. The performance index there is defined as follows. There is extended regret, which is also known as standard regret, where you use only constant functions for comparison. And there is swap regret, where you use linear sort of functions for comparison purposes. And in NFGs, the no-regret learning has led to CCE, and then there is the Bloom-Munsell reduction, which we are using in our work also, but I won't be able to go into the details, where the no-regret-based algorithm, with that, you can end up with a no-swap regret algorithm. And then we'll be using the optimistic follow the regularized leader framework. And so the Markov games, we have heard a lot about it. I'm going to just very quickly show you some of the basic ingredients of this. There's a finite number of agents. We have some work with an infinite number of agents with mean field structures can be used, but I'm not going to talk about it here. And you have a number of steps per episode, and then the finite state space, a finite action space for each agent, and the reward function for each agent. Of course, it's different for different agents, and then a transition function when the agents pick their actions and the state, then you make a transition to the next state. And within each episode, you have a complete formulation how the agents actually operating. So I'm not going to sort of define, because of lack of time, the notion of a correlated equilibrium and coarse correlated equilibrium, but the difference is that in the case of correlated equilibrium, you have to, there is this modification of strategies, and you have to be optimum for each player against when the strategy is modified. And then in the other case, you hold with coarse correlated equilibrium, you hold the marginal probabilities of all the other agents, and then your marginal probability should be optimum given that. So let me just share with you I have just 1 minute, essentially the basic theorem, convergence result. And this is you of course have to introduce a gap there, and you are optimizing this. And if we use the BM OFTRL with smooth value updates on the n-player episodic Markov game, then the gap is bounded by this quantity. So you have 1 over t, and there's a log t here, and you have the dependence on other terms. H is the length of the episode, which is to the order of 7 over 2, and this is the maximum size of the action space. So this is the theorem for the CE, and I'll show you the theorem. You can refer to the paper for all the proofs, some of which are quite deep. And the algorithm that's used for CCE, this is the main theorem. The order relationship is again 1 over t. It's log to the t to the power of 5 and h3 and so on. And this improves the known bounds up to this time. And it matches the best known results for normal form games, except for this factor. Of course, the normal form games don't have the H there. Okay, so you cannot do any better than this. So that's all its conclusion. So we have studied the no regret learning in this paper, and both CE as well as CCE. For CE, we have used BM OFTRL, and for CCE, we have used OFTRL, and in the order of 1/t. And it's a challenge for this community to improve upon the logarithmic part of these bounds. Otherwise, this is a closed chapter. Thank you.
Thank you. I think we have time for a quick question while the next presenter comes up. If not, I can take the liberty. So I noticed that the bounds did not depend on the cardinality of the action space, but just the magnitude. Does that mean extending to continuous state action spaces is a possibility, or will something fundamentally need to change there?
No, they depended on the Amax here is the cardinality,
it is
the
the
maximum cardinality of all the action spaces.
Okay.
So therefore, continuous. I mean, one question, natural question would be, what if you have continuous action spaces? Then you have to quantize it, and then the quantization has to be in that order, and then you have to look into how that contributes into the error.
Yeah.
That's future work.
Yeah.
Yes.
Yeah, very interesting. Okay, let's thank the speaker again. In the interest of time, I'll introduce the speaker while we set up. So our next presenter is Rasoul Etesami, also from UI-UC. He will be speaking on the topic also of Nash Equilibria in stochastic games using online mirror descent. So it's nice to see that even though we lost Sebastian Bubeck to large language models, someone's still flying the flag for online mirror descent.
Thank you very much. Good afternoon, everyone. I would like to thank Tamer Başar for setting the stage for Markov games, because this is going to now be the second talk on games. So this is a joint work with my former PhD student, who is now a research scientist at Alibaba in Shanghai. So basically, the basic question we are trying to address here is that what class of Markov games can we consider in order to be able to come up with scalable learning algorithms for finding their equilibrium points. So in order to define the problem, I would like to briefly talk about Markov games. So in Markov games, we have a set of players, and we have a shared state space, S. At each time t, the players are going to observe the state. Then they're going to take some actions, and they receive some rewards. And note that the rewards depends on the entire state and the actions of all other players. And then the state is going to transit to the next state, st plus 1, based on some transition probability matrix, P. So for practical reasons, we are often interested on simple type of policies, where basically the players just want to take actions by just looking at the current state, and they don't want to restrict their attention to the entire history of the game. So we call such class of policies to be stationary policies. And then by following some policies, and players are going to receive some payoffs, where the payoff is the expected average reward that each player is going to receive over the entire horizon. And an important notion here is the notion of Nash equilibrium, or a stationary Nash equilibrium, which is an action, which is a policy profile pi, such that no player can change its policy and improve its total payoff. Okay? And we call it ϵ-Nash equilibrium if the same property holds within a gap of at most epsilon. So we are interested in finding such kind of Nash equilibrium policies. Unfortunately, this is a very difficult problem, especially for n players Markov games, and there are computational lower bounds that this problem cannot be solved unless you have exponential computational power. So the question we are trying to address here is that is there some reasonable assumptions that we can impose on this game in order to break this computational barrier? And this is something that we are going to focus in this talk. We call it the stochastic games with independent chains and unknown transition probabilities. So the setup is pretty much the same as general stochastic games with this extra assumption that now, again, we have a set of players, and each player has its own state space. So players, again, observe their own states. They take actions, receive rewards, and the state of each player is going to transit to the next state, but this is independent across players. Note that even though the transitions are independent for players, the players are still coupled through their payoff functions because the payoff, the rewards are still function of the entire state and entire actions. So we cannot simply decouple all the players and focus on one of them. So more precisely, we assume that the joint transition probability, which is denoted by P, can be factored in the product of transition probability matrices for different players. And moreover, these transition probability matrices are unknown. So players do not know what stochastic game they are playing. As before, we can define the actual payoff of a player as the expected average payoff for all the players. And then we are going to see whether we can find a Nash equilibrium policy for such class of games. Okay? That's what we want to answer. Great, so what are the applications? This is one simple application of such games. So suppose we have some servers. Servers here are the players. And then servers receive some packets which are generated based on some independent sources. The packets are going to queue on each server, and the servers have to decide whether to transmit their packet through the same channel or not. If yes, with how much transmission power. Since the packets go through the same channel, basically the players share this, the payoffs are coupled, the rewards, because they are going through the same channel. But since the packets are generated from independent sources, the transition probabilities are going to be independent. So there are many other applications for this kind of games, like energy management in smart grids or multi-agent robotic navigations, that for the sake of time I'm not going to go through. Now, in order to design an algorithm to find and to allow the players to learn their equilibrium policies, we are going to come up with a dual formulation for this game, which the formulation relies on occupancy measures. If you were in the first tutorial session in this conference, they had a nice overview of how to deal between the space of policies and the occupancy measures. So the idea is that we look at the frequency of being at different states, actions, and transiting to another state. We call it an occupancy measure. And then we can define a space of occupancy measures, which is going to give us a convex polytope. And then if you give me the occupancy measure, I can generate the policy by just simply normalizing that occupancy measure and vice versa. So the good thing is that if we write this game in the occupancy measure space, suddenly the payoff functions become very nice. And for example, we can show that in the space of occupancy measures, the payoff of each player is going to be linear with respect to its own occupancy measure, and it can be highly nonlinear with respect to occupancy measures of all other players. So that suggests that we can define a so-called virtual game where it's a static, compressed version of the actual game, where now the player's actions is not just to take actions, is to decide what occupancy measures they want to choose. And then the payoff functions are given by this linear transformation that we have. So, and here is a very high-level idea of the whole algorithm that we are going to design. So we start from the original stochastic game, and then we look at the dual formulation of it, which gives us a static game. And this static game, the action of a player is to choose its occupancy measure. So once we design our algorithm in the dual space, we are going to map it back to the policy space by simply normalizing these occupancy measures. Well, while the idea seems interesting, but there are many challenges that one can handle. So for example, the original stochastic game can be repeated infinitely many times, but the static virtual game can be played only once. So we cannot learn over the static game. What we can do, we can use this static game to guide the dynamics toward the equilibrium. Another challenge is that the whole equivalence that we have between primal and dual space here only works if we work with the true transition probability matrix P, which is unknown to the players. And players should carefully change their occupancy measures in order not to destroy this equivalence between primal and dual space. So given these challenges, we kind of come up with an algorithm which works in a kind of interesting way. So the algorithm first ensures that the induced transition probability matrix is going to approximate the actual true probability matrix over time. And then at the same time, the players are going to repeatedly optimize their occupancy measures while ensuring that in the limit they are playing their best responses. So the algorithm has two main parts. The first part is going to construct a polytope for the actual occupancy measure set, which we don't know that. And over time, we are going to make it more and more accurate. In the second part, we are going to use an online mirror descent in order to push these policies toward the optimal policies in the equilibrium. So here is the full description of the algorithm. I'm not going to really go through that, but I just want to mention that it has four major parts. The first part is that you start from an occupancy measure, and then you project to the policy space by normalizing it. The second part is that you play that policy for some time, and then you collect information to construct an unbiased estimator of the gradient of the payoff functions. The third part is now using the information that you collected, you are going to make your occupancy measure polytope more accurate. And then the last part, you are going to use an online mirror descent to project your occupancy measure to the more accurate occupancy measure polytope that you have. And we repeat this process until we get some interesting results. So here is the performance guarantee of this algorithm. It says that under some, if the game admits a stable equilibrium, meaning that the Nash equilibrium policy is globally attracting, then by following this algorithm, the dynamics are going to eventually learn the Nash equilibrium policy in the limit. And that can happen with arbitrary high probability. But can we say something about the convergence rate? And interestingly, this algorithm works reasonably fast and under a slightly weaker notion of convergence. So in order to talk about the convergence rate of this algorithm, we rely on the so-called Nikaido-Isoda gap, which is very similar to what you saw in the previous presentation. It's basically the total gap between payoffs of the players if each time one player changes its strategy. So nice thing is that if we can show that this Nikaido-Isoda gap is less than some epsilon, then it means that my policy is in fact an epsilon Nash equilibrium. So the smaller this gap is, the closer we are to the equilibrium. And this is what we can show. That if you choose any gamma in the interval 0, 1, then with arbitrary high probability 1 minus gamma, by following this algorithm, the average Nikaido-Isoda gap goes below epsilon. So the average gap is going to be almost close to the Nash equilibrium, and that can happen only in polynomial time. So after at most polynomial number of iterations, the average gap is going to shrink below epsilon. So we have kind of polynomial time convergence rate, but again, the convergence is within the distance, the Nikaido-Isoda gap function. All right, so I guess not much time left, so I'm going to conclude. So we basically come up with a decentralized learning algorithm for stochastic games, which converges to epsilon Nash equilibrium policies, assuming that a stable Nash equilibrium exists. And then we showed that this algorithm is going to converge in expected polynomial time with arbitrary high probability in a weaker distance of Nikkei is the function. In fact, by imposing extra assumptions on the reward functions, we can show that this weaker distance coincides with the actual distance to the Nash equilibrium. So I guess this opens, it's a kind of a stepping stone for many other future works in this direction. So in the case of static games, there are many classes of games that people know how to develop scalable algorithms for computing their equilibrium. When it comes to stochastic games, this becomes quite challenging, and there has been some recent works which tries to extend static games to stochastic games. So for example, for static games, we have potential games that we know how to compute the equilibrium under some conditions. An equivalent version of it is Markov potential games that people nowadays are looking into. But still, this is not a very well-explored area, and this is an interesting question that how can we characterize a reasonable and nice class of stochastic games where it admits scalable learning algorithms. So I guess with that, I would like to thank you, and I would be happy to take any questions.
Okay, we certainly have time for some questions for the speaker. Again, while people think, I'll take the liberties. Oh, sorry. Yeah.
Yeah, I think I just had a question about the algorithm. I think that one of the steps involves, I think was it involving waiting for the entire state action space to be explored, or there's one with this random time where all SAs are visited. I was wondering if you could elaborate on that.
Here?
Yeah, the second bullet point.
Right, the second bullet here. Oh, so the lengths of the episodes you're talking about?
Yeah, it says the first random time all state action pairs are visited.
Right. Right. So, so basically, we follow a policy for a random number of iterations until all the states and actions for each player is visited. So the length in the worst case scenario can be very long, but using some Matthews formula, because this is basically the cover time of a Markov chain. So the expected length of it is logarithmic in terms of the number of the states and actions. So the expected length of basically each episode is well bounded by okay. Thank you.
Any further questions? Maybe I can ask just briefly on this slide. Perhaps I missed it. What is the mirror map H in the Bregman divergence there?
Yeah, this can be any kind of strongly convex regularizer that we can choose. And the bounds that we obtain here is for the entropy type regularizer H.
A classic choice. Okay, in the interest of time, let's thank the speaker again and move on. While we get set up here, I'll introduce the next presenter. It's Daniel Ornia from Oxford here, who will be speaking on robustness in reinforcement learning.
Thank you. Yeah, okay, thanks. Yeah, so my name is Daniel. I'm going to be talking about some work on bounded robustness in reinforcement learning that I did. This was done during my PhD at TU Delft under the supervision of Manuel Mazo, but it was done in collaboration with colleagues here in Oxford, and where I'm now a postdoc. So I'm going to be dealing with a very, let's say, simple but quite prevalent problem in reinforcement learning. So imagine we have a traditional MDP setting where we perhaps have a simulator where we're sampling data and we're training an agent. During training, let's assume it's fully observable, so we are sampling states, executing actions, and we're using this to train policy through any policy gradient algorithm at choice, model-free. But let's say that at deployment, we're going to deploy this either in a slightly different simulator, in a machine, in a lab. The most, let's say, simple but yet very destructive form of robustness problem that you can have here is that your states will be slightly disturbed. So your observations, you suddenly go from a purely observable MDP to essentially a form of POMDP that is only observable at deployment. And this may not be fixable at deployment. We may deploy these controllers in perhaps very small devices that don't have the capacity to retrain networks. This is very easy to show that with this simple disturbance, you can cause, let's say, unboundedly bad drops of reward performance in terms of absolute reward. And you can think like by slightly swapping one observation by another, you can cause the agent to execute a completely different action and fall in a pit or break or. So then, yeah, the motivation for this is we're learning to control some kind of system and we have a perfect simulator and we want to make use of this perfect simulator. But we know that when we deploy this, there will be some kind of shift in the observations. There are existing solutions for this, especially if you think of model-based systems, right? Like you could do some filtering at deployment, some disturbance rejection. We want to stay in a model-free realm. And another way that people deal with this in reinforcement learning is via adversarial regularization. So you consider like the worst possible, during training you would consider the worst possible disturbance and then train on that and then deploy that agent in the hopes that that would have robustified the agent against whatever noise you find. There are different problems with adversarial robustness and adversarial training. Apart from the possible convergence guarantee loss that you may find if you start adding adversarial terms in cost functions when training RL agents. You lose your guarantee in terms of how optimal your policy is, for example, if you remove that adversary. So the goals here were kind of twofold and we address them at the same time. So first, we would like to have some kind of framework that gives us a formal bound and a formal trade-off between losing policy optimality and kind of robustifying this policy during training. But we want to do this, or we want to try to do this against unknown disturbances, right? So the whole point is that at deployment, you don't know what kind of distribution your noise will have. And so we want to deal with this, both these problems at the same time. So a small intermezzo. So for this, especially for the first one, if you've heard of lexicographic optimization, it recently was extended by some colleagues to apply for general RL objectives. The idea is that you can have a hierarchy of objectives that you want to optimize for, and this hierarchy is lexicographically more important, like the one from the preview. So for example, I would want to be optimizing for the first objective as my highest priority, and then define some kind of tolerance, some kind of epsilon tolerance, and then all those policies that optimize up to an epsilon, find the one that optimizes for the second objective, and so on. So what you obtain, if you think of like a policy space, is something like this. So if you would have 3 objectives, and the first one is the most important one, I define an epsilon ball, and then I search in this epsilon ball which one optimizes my second one. I draw another ball around this one, and I can keep doing this for n objectives, finding a policy that guarantees this kind of hierarchical optimization, such that it is epsilon optimal in terms of the first one, and from those you've tried to optimize the next objectives as good as possible. So then, very quickly, the formulation, the interesting part of like this simple disturbance is that you can basically push the disturbance in the state space to a linear map on the policies by basically saying that adding a random disturbance to the state is equivalent to considering a stochastic map on the disturbance. So that for a given state, you have a different, you have a probability of measuring different states, thus executing those policies with that probability. And this allows us to write the disturbed policy as essentially like a linear operator, linear stochastic operator on the original policy, which has some nice properties to study what does this mean for the policy space and what does it mean to be robust to noise. So if you would think a possible characterization of robustness would be using some form of regret term and saying that being very robust or maximally robust to a disturbance would be to lose no cumulative reward. So if I found some policy that optimizes the rewards and I know how much I'm getting in expected rewards for a particular problem, and now I disturb this policy, I would say this policy is maximally robust if I don't lose any rewards in this process. So this regret would be 0. But you can find other, let's say, more fine characterizations. So for example, you could think of like an advantage equivalent. So the advantage is usually, the advantage of a policy or of an action is usually measured as the value of that policy minus the Q function, minus the Q value. But in this case, you could think of the disadvantage of this robustness problem, which would be something like, for a given state, I've measured a set of rewards, and if I disturb this policy, I lose some rewards at one particular state, and this can be measured through the Q function. So essentially, you can start defining sets of robust policies that are all included one in each other, depending on how are you characterizing them. So the more general one would be to have policies that have 0 regret. But then you can start focusing and defining inclusions on sets based on these other characterizations, going to the smallest one, which is the one that we use to define some like a robustness objective. So there exists a set of policies that are robust to any disturbance, which is useful if you're trying to robustify policies against any disturbance. It may be quite obvious which set of policies this is the set of policies that are constant across your state space. So if you think that you're applying the same distribution of actions in your whole state space, and I swap whatever state by whatever state, then you'll be executing the same action. So in this sense, even whether it is optimal or not for your problem, that's another question, but in this sense, it is maximally robust. So we can use this principle to basically push policy gradient scheme using this lexicographic approach to robustify the policy against any unknown distribution of noise. And doing this while we preserve some kind of epsilon optimality in terms of the original problem. And the motivation for preserving this epsilon optimality actually has, it can have different justifications, but essentially, for example, if you saw the keynote this morning from Professor Jan Peters, even nowadays a lot of people are encoding safety terms in rewards. So deviating a lot from an optimal observed reward would mean that you perhaps are incurring in unsafe behaviors. So ensuring that your original policy is deviating at most epsilon from optimal cumulative reward also provides some kind of safety filter. So then the idea would be that with this you would choose at training time any disturbance you want that has this property where the fixed point of the disturbance map is as small as possible, which is a constant policy set. And like this, you would guide the policy search towards more robust policies against any other form of disturbance. And this is kind of like the intuition. Again, this is a bit idealized, but the intuition would be something like, on the left, it would be if you would try to like manually tune weights, for example, with robustifying policies versus optimizing rewards. And the idea is that by using this lexicographic approach on top of it, you inflate the set of optimal policies in terms of rewards, and you will at least guarantee that you will convert somewhere in there, and from those you will try to robustify. And this provides a really easy to apply meta algorithm. Essentially, you choose whatever disturbance you want to train against, You can define a robustness loss, and the easiest one is, for example, define the distance between this perturb policy and the original policy. And then you combine the objectives in a classic SGD, stochastic gradient descent algorithm, with these lexicographic weights. For more detail on how these weights are computed, I'll refer you to the paper, but essentially it's 2 timescale learning rates combined with some Lagrangian that is adaptive to how close you are from the estimated optimal in terms of the first objective. And then you obtain guarantees of this sense. So you obtain guarantees in the sense that if you have an algorithm that is guaranteed to converge to an optimal policy in a traditional setting, then it's guaranteed to converge to an epsilon optimal policy, while from those epsilon optimal policies maximizing the robustness. And some interpretation or some conclusions on this particular part of the results. So yeah, this can be applied in principle to any policy gradient algorithm, and we applied it in the experiments to both on and off policy algorithms. You preserve the original algorithm guarantees, so there is also a lot of push in developing RL algorithms that have guaranteed convergence, and in this case, you would be preserving those guarantees. And yeah, the intuition is that what you're doing, for example, as compared to if you're familiar with entropy regularized RL, where the action distribution is smoothened via some kind of entropy term, this has been also observed to increase robustness. In this case, what you're doing is smoothing the policy across the state space, such that any deviation in the states would cause, hopefully, a smaller deviation in your policy, and therefore a smaller deviation in the observed rewards. And this is just a small summary of some experimental results. Again, there is much more detailed results in the paper, but to not bore people with numbers. Essentially, you observe, intuitively what you observe is the middle one is ours, and the one on the right is a baseline that we use that trains adversarial agents. So it trains agents against adversarial noise. What you observe is that it's still training against this form of robustifier, in our case, still is able to actually robustify the policies quite well against adversarial noise. And it does much better when this noise is a much more, let's say, friendly disturbance, like a uniform noise or a Gaussian noise. And yeah, we also tried different kinds of robustness losses that are based on, for example, the disadvantage. And we show that that improves, again, for very mild types of noise, but it doesn't do so for adversarial noise. And yeah, the main takeout is that you obtain comparable results, at least in the experiments tested, to other more aggressive adversarial robustness schemes. And you preserve the guarantees of the algorithm, and you preserve the epsilon optimality of the policies. And this is some a small characterization or a small clip of what actually happening with the behaviors of these agents. So this is what happens if you train a vanilla PPO algorithm and you inject this uniform noise at deployment, and it's very mild, bounded uniform noise, and yet you see that here the agent is rewarded for driving fast, so it learns to like overtake. And you see that as soon as you inject a small amount of observation noise at deployment, it keeps crashing against other agents. And what happens if you apply this lexicographic robustness is that the frame rate is a bit strange, so it looks like they're not moving, but they're moving like essentially at a constant speed. And it's interesting that the emerging behavior here is that the agent learns that it can just lose a little bit of reward defined by the epsilon parameter that we chose in favor of driving essentially at a constant speed with the other drivers, which then reduces collisions even if it has noise in the observations, because it can estimate that, well, I'm far enough from the other vehicle, so then I'm not going to collide. Again, take this with a grain of salt. This is one environment, but it's a interesting one to evaluate the behavior of the agents. Yeah, so we decided to tackle these two things at the same time, trying to robustify RL agents against unknown noise, and doing so preserving some kind of optimality in the policies, and we did this with a lexicographic optimization approach. As in many robustness in RL problems, it's not always clear what is the best option, and in particular, I would argue that perhaps doing this completely model-free, if you're trying to provide any kind of safety guarantees or robustness guarantees, is maybe not the best option. Maybe you would still like to learn a model. But we did this because there is an interest and there is a lot of literature that deals with a completely model-free approach. So I think with this I conclude. And yeah, any questions, I'll be happy to answer.
I think we have time for a quick question.
Thank you for the great talk. Just one simple question. You mentioned that you assumed that linear mapping of the original policy and check all the things. But it seems like you assume that the noise from the state is like a uniform distribution. What about if you have some probabilistic stochastic characteristics? Is it still linear mapping?
So it is actually it's not assuming that we don't assume that you have uniform noise. The reason why you can write it as a linear map is because it's essentially you have a probability matrix that tells you what is the probability of measuring any state from any other state. So it is a discrete distribution of noise, at least in the formulation, but it could be any distribution. So this linear map is linear in the sense that it acts linearly in the policy because it acts as a linear, or it ends up entering the sampling of action as a linear product, or as a product of terms, as a product of policies for different states. But essentially, it is a stochastic map that accepts any disturbance. So you could have like state-dependent noise as well. So at any state, you could have a different distribution of the noise, for example. It just needs to be discrete and time invariant.
So regardless of the type of the noise, you can apply the linear mapping in the like policy and then check all the things.
Yeah, and for the experiments, we assume one. So we assumed, I think in one of the experiments, we assumed uniform noise. But you can also assume other types of noise. If you, for example, you can also interpret it as a prior. So if you have some idea of what kind of disturbance you will end up encountering, you could define this linear map to be something closer to the real disturbance. And it would help, at least empirically, in robustifying.
Thank you.
Okay, great. In the interest of time, let's continue discussions offline, but please join me in thanking the speaker again.
Thanks.
There we go. Awesome. All right, we're using this one.
Okay, great. It's time for the final presenter of the session, Viktor Kolev, joining us from Stanford, who will be speaking on conservative model-based imitation learning.
Thank you, Jack, for the introduction. Hi, everyone. I'm Viktor, and I'm very happy to be telling you about some work that we did at Stanford with Raphael, Kyle, Professor Jajun Wu, and Professor Chelsea Finn on efficient imitation learning with conservative world models. Now, as Professor Weitzman in his keynote mentioned, imitation learning and behavioral cloning are quite desirable ways to teach agents. Learning through imitation is a very good way to imitate complex behaviors. And our goal in this work is to design a way to efficiently learn to imitate complex behaviors from high-dimensional observations. Behavioral cloning is the classical approach to this problem, where we teach an agent to directly copy the expert behavior through maximum likelihood. However, this, as again Professor Weitzman mentioned in his keynote, often leads to covariate shifts and compounding errors, which lead to failure cases. And this is due to distributional shift at test time. Now, the primary reason why these failure cases happen is that the model has not learned any mechanism to self-correct. So we're not robust around the expert distribution we're trying to mimic. And so while behavior cloning is simple and straightforward and works from high-dimensional observations, which is the context we're trying to work in, and it does not require environment interaction, it cannot handle distribution shifts. Therefore, we look at an alternative to behavioral cloning, namely generative adversarial imitation learning. This is an inverse reinforcement learning method, which means that we're trying to learn a reward function here. The reward function is modeled by a discriminator, which tries to distinguish expert trajectories from the agent trajectories. And it fine-tunes the agent with, so it needs to learn from high-dimensional observations, which is a problem since it fine-tunes with reinforcement learning. And reinforcement learning from high-dimensional observations is a non-trivial task. It also, however, needs on-policy rollouts for the said reinforcement learning algorithm that it builds on top of, which further complicates things. And so, while behavior cloning is simple and does not require additional environment interactions, adversarial imitation learning can handle distribution shifts, but cannot handle high-dimensional observations and requires more environment interaction. So the question now is, how can we combine the benefits of both behavior cloning and adversarial imitation learning? Now, ideas from cognitive science, such as world models, posit that both humans and non-human animals develop models of the world in which, through mental simulation, they can learn new behaviors through imagination. And in the context of imitation learning, this seems quite desirable, since we can, instead of requiring these additional environment interactions, we can actually learn our self-correcting behavior inside of a world model. So how might this look like? Well, this is what Professor Weizen, again, was mentioning in his M-Gale, or model-based Gale. So basically what is happening is we're encoding our high-dimensional observations in a low-dimensional state space. And then we do policy rollouts in the world model, inside of that model latent space. This is on policy for the agent, even though it is inside of the world model. And then we use the discriminator to get rewards, and we can train the discriminator and the agent jointly. Note, however, that now the expectation is not on policy rollouts, but is on policy rollouts inside of the world model. So we do not require additional online interaction. And so we have achieved all three desired properties, namely we can learn to recover from distributional shifts and learn self-correcting behavior. This works in high-dimensional observation cases, and we can even train off-policy or offline, i.e. we can learn the world model with off-policy or offline data, and then train an adversarial algorithm on policy with the model rollouts, so without requiring environment interactions. Now, this has all been work that has been developed so far in the literature, but our key contribution is a theorem we prove, where we bound the performance gap between the learned policy and the expert with two terms. The first term is the standard adversarial imitation learning objective, which is a distribution matching. And then we have, and note that this distribution matching objective is inside of the world model, which is why we see the M hat. This is the learned transition dynamics of the environment. But then we have a second term, which accounts for the fact that we're now learning inside of a world model, and so we need to pay the cost that is from the fact that we're no longer working with the real transition dynamics, but rather with learned transition dynamics, which have some sort of approximation error. And so that's the model mismatch term, which is the cost we're paying for using a world model. And therefore, we arrive at the following key insight. Model-based imitation learning is an inherently conservative problem. And conservatism as an idea has existed for a long time in offline algorithms, but hasn't really made its way into on-policy model-based algorithms, since it really curtails exploration. But in the imitation learning context, we actually do not need to do any exploration, since we already have expert data. And so it is much more important for us to be robust around that expert trajectory rather than to explore the environment further. So how might we train a conservative world model? And importantly, how can we optimize jointly this distribution matching objective and the model mismatch objective? Well, we can use a learned latent model ensemble and approximate the model mismatch through the disagreement of that ensemble. We then take that disagreement and add it to the reward as a penalty, which means that we penalize the states and actions in which the latent ensemble has disagreement, which means that they are not well represented in the data. And that leads to this penalized reward, which we use in policy learning. And this approximation of the empirical uncertainty estimate with a latent ensemble is quite a popular choice in the literature. We test this algorithm on two environments. Both are in simulation. The first one is a 20 DOF shadow hand bounding balls task, in which we have a dexterous hand that is trying to rotate two balls. And the second task is the Franke kitchen, which is a long horizon task. Now, these two GIFs are both from learned policies by the algorithm. And note how the Franke kitchen, when trying to turn on the light right now, fails for the first time, but the second time it self-corrects. So this is the self-correcting behavior that we're trying to learn with the adversarial imitation learning. Here are our results. We are comparing our method, CMIL, to one model-based method, VML, and one model-free method, PDAC. Both are from pixels. We see that in Franke kitchen, the model-based method achieves some success, but is about 2 to 3 times less sample efficient than our method, which accounts for the model mismatch term. And the model-free methods completely do not make any progress on Franke kitchen. In the shadow hand environment, which is quite a bit more complex, only our method is able to get any meaningful success rate, with the other methods not able to even match the BC behavior cloning baseline. Now, we're also able to empirically verify the claims of our main theorem. Here on the plots, you can see the performance gap in blue, the distribution matching term as measured by the discriminator is in red, and the model mismatch as measured by the uncertainty estimator, i.e. the model disagreement, is in green. And we see that the underperformance tracks the other two terms quite well. Note that these are unitless variables, so we have normalized them between 0 and 1, and so everything is accurate only up to a constant multiplier. But we see that the trend is matching up with our theoretical predictions. And it's always good to see that these actually hold in practice as well. So to conclude and to let everyone go to the coffee break that we have all been waiting for, we have shown that we can utilize world models for capable imitation learning. But in order to do that effectively, we need to account for the model mismatch cost we're paying for learning inside of a world model. We can efficiently optimize that model mismatch cost through uncertainty estimates, which turn out to be empirically accurate. And this enables high-dimensional efficient control from demonstrations, which was the goal we set out in the beginning. Now, what are next steps and open questions in this? Well, first of all, it is not obvious what the most efficient way to measure uncertainty is. So we used a latent model ensemble, but that is by no means the only choice. There are approaches such as epistemic neural networks, which might be more promising. Another question is, how can we adapt uncertainty estimates for large-scale transformers, diffusion models, or leading physical prediction engines, such as the video prediction engine Sora? And lastly, how can we adapt these ideas to world models that are beyond the physical world, such as using world models as an LLM, or agents that work in digital environments, or theory of mind agents, which need to work with other environments that are outside of their own. And with that, I would like to thank you, and I'm happy to answer any questions.
Okay, any questions for the speaker? We certainly have time.
Yes, thank you for the excellent talk and very interesting work. And maybe this is a control conference, right? And there has been a long history of people in control doing system identification as a sort of way of doing like indirect data-driven control. How would you see this work connecting back to that rich history of, let's say, data-driven indirect control methods? If that question makes any sense to you.
Right, that's an excellent question. So if I am understanding correctly, what you're asking is, how can we tie this work back to the long history of control works that have existed in the space?
Yes, I mean, I'm coming from a more, let's say, classic control background, right? What I would do if I have an unknown system and I want to do maybe, I don't know, track some trajectory that an expert provided, right? I could look at the evolution of that system over time, fit some model, like gray box model, black box model, whatever, to model the system dynamics, and then design, let's say, an optimal controller to steer my system according to that system model that I learned. Right?
Okay. So two things here. Number one, the environments we're working with, first of all, are completely from pixels. So we only provide 10 demonstrations and work entirely from pixels, so there is no state that is being given to the system. And so that state estimation task is hard in itself, especially for the shadow hand environment. That's a 20 DOF dexterous hand. The state estimation for that is really non-trivial, right? And so that's one aspect in which implementing classical control would be pretty hard, I would assume. The second point I would like to make is that, for instance, the Franke kitchen environment, that's a really long horizon task. We have 4 tasks that we need to execute in a particular arrangement. And so that, I would assume, would also be quite difficult to do with classical control, since it's not really a, how they put it, a low-level control task, but rather a much more higher-level planning task as well. Does that make sense?
Sure. Thanks.
Thank you. Thank you for the question.
Any further questions? Maybe while folks think, I can also ask, in the bound that you presented, is there some hidden dependence on the underlying robustness of the expert policy? There's been some kind of prior work that maybe roughly speaking shows that the more robust the expert is, the easier it is to imitate it. Is that hidden here in one of these terms in the bounds, or does that show up?
Right. It is sort of hidden in the distribution matching objective, which is quite a classic. I mean, we are here working with the underperformance to the expert. So this performance gap is to how well this expert policy is. So obviously, through simple imitation, we cannot do better than the expert we're trying to imitate, not with additional reinforcement learning. And so it is hidden both in the performance gap to the expert and in how easy this distribution matching objective is to optimize. With a more robust expert or with just more expert data, that objective is a lot easier to optimize. And so you can think of it as, you can shrink it to near zero. But in a more data sparse environment, or when the expert is more stochastic, then that just might be a harder thing to optimize.
Yeah. Okay, yeah, I think that makes sense. Great. Any further questions? Okay. I don't see any hands. So if not, let's thank the speaker and indeed all our speakers one more time.